exponential functions is what this section is about. And this is what exponential functions look like. F of x equals a to the x. The base is a, which is going to be a constant. A has to be greater than 0, but it can't be 1. Okay. So for example, here, so compare this with this. Here we have a is 4. This is number 1 is an example where a is 4. So the base is 4. So the base is a is 4. Then you're also evaluating at different points. So f of -2, that would be 4 raised to the -2. So now remember, when we raise to negative exponents, it's 1 over 4 raised to the positive, corresponding positive exponent. So it's 1 over 16. That's what's going to go in here, 1 over 16. F of 0, that's going to be 4 to the 0, which is just going to be 1. Okay. F of 2, that's 4 to the 2. So you're just replacing this x with a 2. Okay. So the idea is that, like, over here, this x got replaced with a 2. So then, like, this x is like, well, you replaced me with a 2 also. So that's going to be 16. And then right here, this is 4 to the 6th. So that's actually 4 times 4, 6 times. But, you know, calculators can also do powers. But anyways, this is going to give you 4,096, pretty big number. So exponential numbers, when you start putting larger numbers in the exponent, it goes up pretty fast, pretty quickly. That's where the exponential growth comes from that term. Okay, now as far as graphing, let me just briefly explain graphing, and then we'll get to some of it. So graphing, and I like to do this. Okay, I'm going to make a little chart right here, x, and f of x equals a to the x. And there's 2 values of x that are pretty easy to do when you're doing this. The first one is 0, because a to the 0 is just going to be 1. And a to the 1 is going to be a. So this gives 2 points on the graph already. Okay, 0, 1, and 1a. Okay, now let me split it up into 2 different cases. Case 1, where a is greater than 1. Now remember, a has to be greater than 0, and it can't be 1. So case 1 is where a is greater than 1. Case 2 is where a is between 0 and 1. Okay, so those are 2 different situations. Okay, so in this one right here, what's going to happen is, of course, this point's going to be on the graph, so 0, 1, right there. Then over here at 1, you're going to be up at a. So a is greater than 1, so let's put a up here. And so it'll go through that point, and then the rest of it will fill in like this. Ah, that's bad. Yeah. And the x-axis, okay, or y equals 0, is horizontal asymptote. Okay, so the x-axis, or the equation, the line y equals 0, is a horizontal asymptote. Okay, over here in case 2, what happens with case 2 is, again, you still have that point 0, 1, but now a is between 0 and 1. So when you go to plot this point, let's say a is right there, it's going to be down here. And what will happen is this will go down like that, and this part of here will go up. Okay, so that's how it looks. So again, the same thing, y equals 0. is going to be a horizontal asymptote. So that's in both cases. So y equals 0 or the x-axis in both cases is going to be a horizontal asymptote. Here it qualifies because as you go to infinity, it goes to 0. Here it qualifies because as you go to negative infinity, it goes to 0. Okay, so those are the two different cases, and it comes from plotting these 2 points. Okay, there's 1a, here's 0, 1. Okay, here's 1a, here's 0, 1. Those 2 points which we said from the equation. Okay, so let's go to some of the exercises where we apply this information. Number 2, match the exponential function with its graph. Okay, so this one, this one was where you have f of x equals a to the x, where a is a positive number, where a is greater than 1, I'm sorry, where a is greater than 1. So that's going to be this one. So this is going to be graph 3 right here. Okay, so that's going to be graph 3. Then this is that one where it's less than 1. Okay, so if you look at this one right here, this one's going to be graph 1. I'll explain why. It's because this right here, 2 to the negative x is the same as 1 over 2 to the x, okay? Which is the same as 1/2 raised to the x. So here a is 1/2, and it's between 0 and 1. So that means it looks like this one. Okay, so like if you look at the previous page, it's that right there. Okay, so one thing to note right here. Okay, this also is what happens when your graph is like wait a second, let me not do that. Okay, this is also what happens when you're graphing this right here, a to the negative x, and a is greater than 1. Okay, so if a is greater than 1, but it's a to the negative x, then it's going to look like this. Okay, so that's just really similar to that. Okay, and so that's like, because, like I said, this is really the exponential with base 1/2, which is between 0 and 1. Okay, and then, of course, if you take this one and you reflect it, you're going to get this one. So it's a vertical reflection, so that's going to be this one. So this right here is going to be this one. Okay, that's going to be 2, because you're just reflecting it. And then this one right here, you're reflecting this one. So that's going to be 4. Okay. Let's move on to number 3. Now here, they're applying transformations. So 5 to the x minus 1. We start with the graph of 5 to the x and we shift it. And then this one's going to be downwards. Downward 1 unit. Okay, because this is downward. This is outside and minus 1. So it's going to go down 1. Okay, here, if you notice here, this minus 1 is up here with the x. It's actually up in the exponent. It's not subtracted afterwards. So this is inside. So inside means it's horizontal and in the opposite direction. So it's going to shift it to the right by 1 unit. Okay, so minus, instead of going left, minus goes right when it's inside. Okay, and then number 4. Let's move along to number 4. The exponential 1/5 of the x has, okay, so you're going to have a horizontal asymptote at y equals 0. That's what I said in the first page. This means as x goes to infinity, we have this goes to 0. Okay, so this right here is the same as the first case that I had right here. As you go to infinity, it's going to 0. So if this a was 1/5, it might be a little bit lower. Still going to do the same thing. Okay, let's look at number 5. Okay, this is 1/5 to the x plus 6. This is outside. Okay, so now what happened here with this plus 6 shifted everything up. And so now the horizontal asymptote is going to be y equals 6, because everything was shifted up. That means that the horizontal asymptote shifts from 0 up to 6, up to y equals 6. And as you go to infinity, you're going to go to 6. Okay, so this is shift upwards by 6. And then this is outside, by the way. So it's vertical is the change. Okay, number 6. Use a calculator to find these values. Okay, so let's go. Let's do that. And it also says round to 3 decimal places. Okay, so let's work them out first. Okay, so it's going to be 3 to the 1/2 minus 1. Okay, so that's 3 to the negative 0.5 is what that is. Okay, this one is going to be 3 to the 2.5 minus 1, or 3 to the 1.5. And then this one is going to be 3 to the negative 1 minus 1, or 3 to the negative 2. And then this last one is going to be 3 to the 1/4 minus 1, or 3 to the, let's see, 1/4 minus 1 is negative 0.75. Okay. So so you can use Geogebra as a calculator. So I'm going to go over to Geogebra. And let's see. It doesn't matter. I guess you could choose any of the calculators, and it would still be the same thing. Okay, just over here, we're going to use this part as a calculator. There's probably not going to anything show up over on the graph. So the first one is 3 to the negative 0.5. And so I hit enter, there's our answer. So this is going to be 0.577. And the next one was 3 to the 1.5. So put 1.5 in there, and there is 5.196 will be that one. The next one is 3 to the negative 2. Oops, no. So 3 to negative 2, that's 1/9. Okay, so now it says round to 3 decimal places, and I don't know how to make this. Oh, I can do this and click this little thing here. It looks like there we go. That's 0.111. Okay, and then f of 1/4, that was 3 to the negative 0.75. That's 0.439. Rounds up to 0.439. Okay, so great. So let's go back and put those answers into. Actually, I got to go back to the document. Okay, so let's go back to and put in what we found. Okay, so we used Geogebra. I should say from Geogebra. So this is an approximation, 0.577. That's approximately 5.196. This is approximately 0.111, and this one's approximately 0.439. I guess I could put zeros on the front as well. Doesn't matter. That's optional. Okay, great. Any questions about that? Okay, let's go to the next exercise. And here, we're supposed to make a table and graph it. Now, this is going to be the graph of, let's see, y equals 7 to the x. So we already know that it's going to be this one right here, because it's going to start out and go up like that. That'll be this one. Not these other ones, none of these other ones. This one right here could be, this could be y equals 7 to the negative x. It could be. Okay, or AKA 1/7 to the x. Okay, that's what this one could be. Okay, but this is going to be the answer there. Now, you're supposed to do a table of values. Okay, so here, it's 7 to the x, so it's 7 to the negative 2. That's going to be 1 over 7 squared, which is 1 over 49. Okay, so the first one is 1 over 49. That's divided by. Okay, and then this one right here is 7 to the negative 1, which is 1 over 7 to the 1, which is 1 over 7. Then 7 to the 0, that's just going to be 1. 7 to the 1 is just 7. And 7 to the 2, that's 49. Okay, so 49. Okay, so that gives us different points. So for example, if I look at this one, 0, 1, okay, 0, 1, that should be right here. That should be the point 0, 1. Okay. 0, 1. Ah, that's really sloppy, 0, 1. Let me see if I can do better. 0, 1. And then the point 1, 7. That looks like it could be 7 because 20 is all the way up here and halfway is 10 and it's a little less than halfway. So that could be 1, 7 and so on. And then you'd find all the other points along this curve as well. Okay, that's kind of what they're getting at right there. Okay, let's look at number 8. Find the exponential function f of x equals a to the x whose graph is given. Okay, so we know that it goes through, here it's going to go through 0, 1. That's no matter what happens. It goes through there. There's isn't really needed for me to do that. Okay, but we also know that it goes through negative 2, 9. Right here. So this point here, we know that a to the negative 2 equals 9. Or maybe I'll do it this way, okay? So we have f of x equals a to the x, okay? This is x is negative 2. And this part right here is telling you that f of negative 2 is 9. Okay, so this is 9. Is a to the negative 2 is 9. Okay, now this is the same as 1 over a squared. And I can also take reciprocals of both sides. Or if I just have that, I can just have them swap places. So a squared is 1 over 9. So that means a has got to be 1/3. Okay, so this should be 1/3 to the x. Now in Webassign, when you do this thing, it goes up a little ways, not as high as you want it to go. So it looks kind of weird, but you know, in reality, this should be way up there. Okay. Okay, let's move on to number 9. graph the function. So you want to graph 3 to the negative x plus 1. Okay, so let me rewrite this in case anybody can't see. 3 to the negative x plus 1. Okay, now here, up here, 3 to the negative x is the same as 1/3 to the x. And it's actually, it's this one right here, this green graph. So it's this graph right here. Right here. So this one right there, the green one, is, no wait, is it green or is it blue? Maybe it's the blue. Maybe that's blue. That's weird. No, that's green. Okay, that's the green one, and it goes down, and it goes right here. Okay, this is the green one. Okay, so this one right here is this graph, y equals 3 to the negative x. Okay, but we have 3 to the negative x plus 1. This is outside. This means up, move up 1, or shift up 1. Okay, so you take this guy right here and shift it up 1, you're going to get something like this one. You're going to get this graph right here. And yeah, so it's also asking for the domain, range, and asymptote. So the domain is negative infinity to infinity. The range goes from 1 to infinity, okay, because you don't have any values down here. No values down here. And y, for this graph here, y equals 0 was a horizontal asymptote, but since it shifted up by 1, the new horizontal asymptote is y equals 1. Okay, y equals 1 is the new horizontal asymptote because this has shifted everything up by 1. Okay, great. Let's look at number 10. That's more of the same. So here we have, so this right here, I mean, it's kind of small here. I couldn't make it any larger without splitting it across multiple pages. But this is h of x equals 3 to the x minus 3 plus 1 is what you're after. And so you start with y equals 3 to the x, okay? Which is going to be, it's going to be the black one. 3 to the x is this black graph here. Okay, so what you're going to do is this minus 3 is going to shift it left. No, shift it right by 3 because it's inside. And then the plus 1 is going to shift it up by 1. Okay, so take this black graph, shift it left by 3, and then up by 1, and you're going to get this one here. No. I said left. I should have said right. Okay, shift it right by 3 because it's right here. Shift it right by 3 and up by 1. So it's going to be this answer here. Okay. So for example, over here, this one goes through the points 0, 1, and 1, 3. Those are 2 points that are on this graph. If I shift it up by 1 and right by 3, then that's going to go to the point. So up 1, so that means you add 1 to here. So that's 2. You add 3 to that one, so 3, 2. So it's going to go through 3, 2. This one right here, you shift it right by 3. That's going to be 4. and this up by 1, 4, 4. Okay, so it's going to go through those 2 points. So 3, 2 is right here. Okay, there's 3, 2. 4, 4. 4 is over here, and then 4 is up there, is right here. Okay, so those 2 points. And then, of course, the horizontal asymptote is going to be y equals 1. Okay, so it's also asking for the domain and the range. So the domain will be from negative infinity to infinity, and the range will be from 1 to infinity. And then the horizontal asymptote is, again, y equals 1, because you shifted up 1. Okay. Okay, so now we get to do some fun stuff. It's also related to exponential functions. This is compound interest. Okay, here's the formula for compound interest. Let me introduce it to you. P stands for the principal. It's also known as the present value in some situations. So a lot of financial people will use that word, present value, to denote P, but it's also principal. Both those words start with P, so there's no problem. R, the R is the interest rate per year. It's not per month or anything. It says it's the overall, it's the yearly interest rate. N is the number of times interest is compounded per year. Let me see. I'll write the number somewhere. This is number of times compounded per year. Okay, and then that's N. And then T is the number of years. A of T stands for, and then A of T, which is the right-hand side of the equation, I mean the left-hand side of the equation, is the amount after 2 years. So it's the final amount. It's not the interest, it's just the final amount. So if you had, let's say you had like $500 and you invested it for a number of years and you ended up with $600, you ended up with $100 interest. Okay, so A of T would be 600. Okay, it wouldn't be 100. It would be 600 because like you still have your initial plus the interest. So 500 plus 100, that's going to be 600. Okay, so then they give you an example. So if $200 is invested at an interest rate of 7% compounded quarterly, then the amount after 2 years is blank. Okay, so this right here is how much is invested. That's our P. P is 200. Okay, interest rate is 7%. R will be 0.07. So you have to convert this from percentage to a decimal, by the way. Quarterly, that means 4 times a year, every quarter. So that means the N is going to be 4. And then here, and then 4 years, that's going to be T. T is 4. T is the number of years. T is the number of years. Okay, so you take this formula here. P gets replaced with 200. R gets replaced with 0.07. N is 4. And then N times T, that's, we can go ahead and multiply these together. That's going to be 16. Okay, now let me show you how you can calculate this. We can use Geogebra for this part. Okay, so I'm just going to put in what we had there, which was 200 times 1 plus 0.07 over 4, and I use the arrow, and I raised to the 16th power. Okay, so I get $263.90. So this is 0.985. You're going to round that up to 99. So 263.99. You always round to the nearest cent. Okay, so coming back to here. So from Geogebra, remember 263.99 is what it rounded off to. Okay, now when you do these problems, I highly suggest that you think about what you're doing. Think about, pretend that this is your money, $200. Okay, you have $200, and you invest it, and for 4 years. So you don't have use of the money for 4 years. And at the end of 4 years, you have $263.99. Okay, so would that be reasonable? Okay, that sounds reasonable, right? So you have $200, and at the end, you have more money, right? So, okay, that's great. That's reasonable. So sometimes, you know, you might make a mistake, and someone might, it's kind of interesting because sometimes students will make mistakes with this, and it's $200, and then they ended up with like $100 at the end. And you're like, you should think of this as $200 as your money. If you invest that, and it's supposed to be earning 7% interest, they tell you, oh, you're getting 7% interest, but then you end up with less money than you had to start out with. Then what's up with that? You're not getting 7% interest. They're taking money away from you. You're losing money. Okay, so you know you should kind of think about what's going on here. Same thing if it's a borrowing money or whatever. Okay, so so let's go on to the next exercise, number 12. So $4,000 is borrowed at a rate of 5.75% interest per year, compounded quarterly. So let's kind of get through everything here. So this means that our R is going to be 0.0575. So just move the decimal place over 2 spots to the left, and there you go. Compounded quarterly, that's quarterly again. So that means N is going to be 4. If it was monthly, then N would be 12, by the way. Okay, find the amount due at the end of the given number of years. Okay, so here, oh, and this right here, I'm sorry, this is P. P is $4,000. Okay, so we're going to apply this formula to all of them. So that's going to be 4,000 times 1 plus, and then you have 0.0575 over 4. Okay, now here's the difference. So the first one is going to be 4 years. So that's 4 times 4, that's 16. Okay, so the first one's 16. The next one will be the same, except 6 times 4 is 24. Okay, so 6 is T is 6, N is 4. So 4 times 6 is 24. And then this last one, T is 8. T is 8. So we have NT will be 4 times 8, which is going to be 32. Okay, so that's what you get for those ones. So let's go over to Geogebra. And we can just put it in right here again. 4,000 times 1 plus 0.0575 divided by 4. And then I'm going to raise that to the 16th power. And that's 5,026.16. Okay, so maybe that sounds reasonable. $4,000, you borrow $4,000, or you lend someone $4,000, and at the end of 4 years, you have to pay back this much, 5,000, or they have to pay you 5,000. Okay, and $26.16. Okay, so that's going to be the answer to the first one. The second one was 6 years, so we decided to put 24. I can just change this to 24, and there we go. So 5, 6, 3, 4, 10. That sounds reasonable. It sounds like it could be. And then the last one was 8 years. That's 4 times 8 is 32. So just change that to a 32, and you get $6,315.50. Okay, this 7 is going to round up to an 8 because you have a 9 there. So $6,315.58. Great. So let's go back to the PDF document, and we'll put the answers in. And the first one was $5,026.16. The second one was $5,634.10. And the third one was $6,315.58. And these are from Geogebra. Okay, so those are going to be the 3 answers. Now remember, you always round it off to the nearest cent when you're talking about money. It doesn't make any sense to go any further than that. Okay, let's look at number 13. The present value of a sum of money is the amount that must be invested now. It must be invested now at a given rate of interest to produce the desired sum at a later date. Okay, so here's the formula. A of t equals P times 1 plus R over N to the NT. This is the formula for compound interest that we just used in the previous 2 exercises. And the problem says, find the present value of $10,000 if interest is paid at a rate of 8% per year, compounded quarterly for 4 years. Okay, so this right, what they're telling you here is that this $10,000, this corresponds to your A of t. It corresponds to this part of the equation. Okay, so so we look at this equation here. This 10,000 is going to go in for that. Okay, it's going to go in for that one. And they're telling you that you want to find the present value. That's going to be P. So you want to find out what this P is. Okay, now you also know that the rate is 8% per year. So that's R is 0.08. And you know it's compounded quarterly, so N is 4 again. Oh, yeah. Can they choose something different than 4? And T is also 4. Oh, everything's 4. Interesting. Okay, so we have 1 plus 0.08 over 4 to the 16. So N times T, that's 4 times 4, so that's 16. Okay, so we plugged everything. We plugged that in for R, which gives you 0.08. We plug in a 4 in for N, which gives you, that's not 0.4, it's 4. I don't know where that point came from. Okay, so if we just take all of this to the other side underneath, then we have $10,000 divided by 1 plus 0.08 over 4 to the 16th power. Okay, so let's go over to Geogebra. And we'll just input that in. So that's $10,000 divided by 1 plus 0.08 divided by 4. And that's, and use the arrows to get outside and then raise it up to the 16th. Okay, so $7,284.46. Oh, that's interesting. Okay, so let's go ahead and put that back into the other one, other document. So $7,284.46. Okay, so that's what, if you invested that much money right now at 8% interest compounded quarterly, then in 4 years you'd have $10,000. Okay, so there you go. Now, I usually do when I talk about this one, I usually do like a little experiment here. So I'm going to say, just kind of a thought experiment for you guys to think about, okay? So let's suppose that we had, let's say $1,000, okay? Let's say you had $1,000, and let's say that you're going to invest it for 40 years. So I just wanted to kind of show you what happens when you do this. And let's say that we have it's compounded monthly. Okay, so that means that, okay, so that when we identify everything, then that's our T is going to be 40, and our N is going to be 12, because compounded monthly, that means 12 times. There's 12 months in a year, so the N is 12. Okay, and then we want to find, and then I'm going to do different cases. So let's say the interest rate is, let's say that we do 1%. Okay, 1% interest rate, and then we're going to do 4% interest rate, and then we're going to do 10% interest rate, and then we're going to do 20% interest. And I show you what happens in each case. Okay, so 1% first. Okay, so plugging everything in, so it's P times 1 plus the interest rate is here. Here, the interest rate is going to be 0.01, so it's going to be 0.01 over 12. And then 12 times 40, let's see, what's 12 times 40? Okay, that's 480. In fact, we can just calculate all these out here. Let's just calculate them all out for just a second. So this will be 1,001 plus 0.04 over 12. All right, so the 480. Here, you're going to get 0.1 over 12 raised to the 480. And here, you're going to get what, 1.2 over 12 to the 480. Okay, so that's the only difference. Okay, now we'll go to Geogebra to figure this out. Okay, so here's the first one. Okay, so you have $1,000 and you invested at 1%, that's a 0.01 there, for 40 years, then at the end you're gonna have you're gonna have like $1,500 at the end, right? Now, after 40 years, this kind of begs the question, you know, how much is $1,500 going to be worth in 40 years? Okay, so there's probably going to be inflation, and it's probably actually going to be worth a lot less than $1,000 today. So $1,500 in the future, 40 years in the future, is probably going to be not worth that much. It's probably going to be worth a lot less than $1,000 today. Okay, so so there's that. Okay, now let's do 4% interest and see what happens. And here we have almost $5,000, so $4,939.87. Okay, so that's going to be worth a lot. We're talking in 40 years from now. And now let's do 10%. And here you see $53,700. Okay, so that's, I mean, what's the difference? There's a big difference between, let's say, you're doing 1%, which is this 1491 stuff, and 10%, that's $53,000, $53,700. That's a lot more. Now, if you do 20%, then here with 20%, you have $2,790,748.47.99. So you got a lot more. Okay, so it's just crazy. Okay, let me see here. Now let's go back and I'll input all the answers and over here. Okay, so just a second. I gotta move these around a bit. Okay, so the first one, this is from Geogebra. So the first one, so 1% was $1,491.58. The second one was $4,939.87, and the third one was $53,700.66, and then the last one was $2,790,747.99. Okay. So here's what can we learn from this? Well, the first one, that would be like, this first one would be like if you just like had your money sitting in the bank. So if you had like a whole bunch of money just sitting in the bank, you know, then $1,000 would get you 1,491. Okay. The second one is if you were to do a mortgage on your house or whatever. Okay, so if you were to take out a mortgage and pay this much interest, okay, like a 4% interest, you know, that's manageable. You know, you got $1,000. It's gonna, if you're doing it over, mortgages are typically 15 or 30 years. So if you're doing over 15 or 30 years, then that's doable. So that's a good. So buying a house is generally a good investment. 10% would be like aggressive, and also you need a little bit of luck investing. And so this is like aggressive and maybe some luck in there. And so like if you're looking at so rather than having money sitting in the bank and just like earning just a little bit, which in the end you're just gonna lose. If you get to the point where you got a whole bunch of money left over, rather than just letting it sit in the bank, you should either think about buying a house with it, or, you know, doing some investing in it with it. Okay, because then if you invest it, then at least, you know, you can get quite a bit of money back. Okay, if you're going to need the money though, then you want to leave it maybe in the bank, or maybe a conservative investment that's not going to earn as much interest. But if you're just going to let it sit there if you're just going to let a bunch of money sit in the bank for 40 years, then you're better off just trying to take a risk with it, because, you know, the payoff can be huge. Okay, 53,000, that's a big difference between 1,500. And then this last one right here, 20%, this is like credit card debt. These are the interest rates that credit cards will charge you. So you want to avoid this like the plague, okay? Because this is like, they're talking $2.8 million from just $1,000 in 40 years. So you don't want to be, so credit cards are fine, but you just have to pay off the balance every month, so you don't pay any interest. As long as you pay all the balance off every month, then you don't pay any interest. And, you know, a lot of credit cards will give you like cash back, or give you points or something, or miles for airlines or whatever. And so those are good things to have, but you don't want to ever carry a debt on it. Okay. You know, credit card companies will make enough money off of you if you're not carrying debt on it, because they take a percentage of whatever, like you buy something from, let's say you buy something worth $100, okay, from a store with a credit card. Then the credit card just going to pay the people at the store. They may have an agreement, so they might pay them only $95 of that 100, and then the store is fine, because they get a good amount of the money, and they're fine with that. And then the credit card might kick you back a little bit. So the credit card companies make enough money without you having to carry a debt on it. Okay, so you want to avoid that at all costs. Okay, so that's